In this video we're going to look at the development of the atomic model. So we're going to start with John Dalton's model. It's quite simply a sphere. So John Dalton proposed that atoms were the smallest indivisible part of an element. The elements contained only one type of atom, and that different elements had atoms with different sizes and masses. Now, all three of those things are still true. If you were to take any element, let's take for example sodium, the smallest part of that is still sodium would be one atom of sodium. As soon as you break it down into its subatomic particles, into its protons, neutrons and electrons, it's no longer sodium. What makes it sodium is the number of protons in the nucleus. So atoms are still the smallest indivisible part of an element. Elements do only contain one type of atom. If you had pure hydrogen, it would only contain atoms of hydrogen, and all of those atoms would have the same number of protons. If you had pure magnesium, it would only contain atoms of magnesium, and all of those atoms would have the same number of protons. So even though he didn't know about protons, neutrons and electrons, these statements were still correct. And this model was only really challenged upon the discovery of the first subatomic particle. And the first subatomic particle was discovered by J.J. Thomson. Okay, and he discovers the electron. So this is our first subatomic particle that has been discovered. And you don't need to know the details of the experiment, but essentially he was experimenting with charged particles being fired through an electric field. So what he was doing was he was firing charged particles through an electric field. So here we have our contacts for an electric field, and he was firing his charged particles through that electric field. And if the particles were negative, then they would be repelled by the negative plate and attracted by the positive plate, so they'd deflect this way. And if they were positive, they'd be repelled by the positive plate and attracted by the negative plate, so they would deflect this way. And how much they deflected depended on their mass. So what he discovered was a particle that deflected nearly 2,000 times more than the lightest known particle at the time, hydrogen. So Thomson found a particle that deflected 2,000 times more than the lightest known particle at the time, which was hydrogen. So what he discovered was the electron, and from this experiment they knew two things. Number one, it was 2,000 times, approximately 2,000 times lighter than hydrogen. So things that they knew: it was approximately 2,000 times lighter than a hydrogen atom, and the second thing they knew, by the fact that it was repelled by the negative plate was that it had a negative charge. And this led to the first significant atomic model that you need to know. So here we have a timeline of the atomic models. So we've got our discovery of the electron by J.J. Thomson. And that brings us to this model here. Now this model is called the Plum pudding model. Because it looks a little bit like a plum pudding. A plum pudding is sort of a sponge cake with bits of plum in it. Sometimes it is compared to perhaps a cookie or a muffin, a blueberry muffin. But essentially what we have is a sphere, and we now know that those atoms contain subatomic particles. We know they contain electrons. So for the first time we've got a subatomic particle. We've got these negatively charged electrons. Now J.J. Thomson knew a few things. Number one, we still thought that atoms were spherical. We now know that they contained negative electrons, but something they also knew was that atoms had no charge overall. So if we knew they contained negative electrons, but overall they had no charge, then that must mean that there was something in the atom that was positively charged. So J.J. Thomson suggested that we had negative electrons scattered randomly in the atom, and that the rest of the atom was made up of a positive sphere to cancel out the negative electrons, so that overall the atom had no charge. So in the plum pudding model, suggests that the negative electrons are randomly scattered in a sphere of positive charge, giving the atom no charge overall. Now, that was the accepted model for a while, and then one of J.J. Thomson's students, Ernest Rutherford, started carrying out experiments to test this theory. Now, his experiment was called the alpha scattering experiment. And this was carried out by Ernest Rutherford. And it's reasonably simple. What he was doing was he would take a thin sheet of gold that was as close to being one atom thick. So essentially he had atoms of gold. And what he was doing was he was bombarding them. If I just label that, so that's a gold atom. And he was firing alpha particles at it. Now, if the plum pudding model had been correct, then these alpha particles should have travelled straight through the atom and then been detected on the other side. So he had a detector. He actually had a detector set up in a circumference around the atom. And it actually went all the way around. So he's firing alpha particles at this atom of gold, or these atoms of gold. And if the plum pudding model had been correct, then every single one of those alpha particles would have travelled through and been detected here. And what he found was 99.9% passed straight through. And what he could conclude from that was that therefore the atom is mainly empty space. Because these alpha particles didn't bounce off of anything, they just travelled straight through. However, they didn't all pass straight through. Approximately every 1 in 8,000 didn't. Every 1 in 8,000 hit something and was deflected. So 0.01% were deflected by something dense and positive. And what they concluded from that was that there must have been a dense positive area inside the atom, and that became the nucleus. So, just to recap, so the alpha particles were fired at atoms of gold. The vast majority of them passed straight through, showing us that the atom was mainly empty space. However, 1 in 8,000, or 0.01% approximately, were deflected. And because of the angle of their deflection, they were able to work out that whatever they were hitting was in the dead center of the atom. Okay, so some of those alpha particles were deflected straight back, which means that whatever they were hitting must have been in the dead center of the atom. So they knew that in the center of that atom there must be a very positive, very dense center, and what they discovered was the nucleus. So if we look at the model, we have our positive nucleus. Now, what's in the nucleus that was positive is the protons. They didn't know that initially, but they did eventually name the subatomic particle that was in that nucleus as the proton. We still have our negatively charged electrons. Only now, instead of them being randomly scattered, they're in these orbitals. They orbit the nucleus. So the majority of the atom is empty space, which is backed up by the results from the alpha scattering experiment. So the alpha scattering experiment provided evidence to suggest the atom had a dense positive center, which was named the nucleus, and that the majority of the atom was empty space. So now we have a positive nucleus, and our electrons are now orbiting that nucleus because the majority of that atom is empty space. Now, later on, Niels Bohr discovered that these electrons didn't just randomly orbit the nucleus. Actually, they existed in energy levels, which we now call shells. So Niels Bohr suggested that electrons occupy different energy levels orbiting the nucleus. And this was significant because for the first time the electrons weren't all randomly scattered or randomly orbiting the nucleus. They were in distinct energy levels, so some electrons had more energy than others. And this tied in quite nicely with patterns of reactivity, and it kind of explained why different atoms could have very similar reactivity, because they would have had electrons in, or the similar number of electrons, or the same number of electrons in their energy levels. So the next discovery was made by James Chadwick, the discovery of the neutron. So they already knew that the atom was heavier than it suggested. They roughly double the mass based on the protons. So they knew there was something else in the nucleus. And actually this was the last subatomic particle to be discovered. So the discovery of the neutron helped to explain why atomic mass was higher than the number of protons. And also, significantly, it explained why some atoms of an element could have different masses. So how some atoms of an element could have different masses, and these are called isotopes. So atoms of an element that have the same number of protons but a different number of neutrons, giving them a different mass. So these models, so in the Bohr model we still have a positive nucleus, we still have negative electrons, but now we have shells for the first time, energy levels that those electrons go into. And finally, after the discovery of neutrons, we now have the full picture. We now have all three subatomic particles. So we have our shells of negative electrons, we have positive protons, we have neutrons, and the protons and the neutrons are found in the nucleus, while the electrons are found in the shells orbiting the nucleus. So just a quick recap. So the first discovery was the electron. So this is our first subatomic particle. And then there's the alpha scattering experiment by Ernest Rutherford, discovering protons in the nucleus, which is our second subatomic particle. And then James Chadwick discovering the neutrons, giving us our third subatomic particle. So for what you need to be familiar with these models. You certainly need to be able to label them and explain them, and in particular you're going to need to be able to explain the plum pudding model and the nuclear model, which is this model here. Okay, now these are the two models that you will be asked about most frequently, and importantly you need to know the alpha scattering experiment. How did we get from this model to this model? You need to know how this model came about. So from the discovery of the electron came about this model, the plum pudding model, and then after the alpha scattering experiment we developed from the plum pudding model to the nuclear model proposed by Ernest Rutherford. And another thing you will commonly be asked to do would be to compare the plum pudding model to the nuclear model. So if we make a quick double bubble map between those two, so we're going to have plum pudding on the left, and we're going to have nuclear on the right. So these are our two models. So we'll start off with what they have in common. So the plum pudding model has negative electrons. The nuclear model has negative electrons. They both have something positive. The plum pudding model has the positive sphere and the nuclear model has the positive nucleus. So they do have a positive charge. Positively charged, I'm just going to say section, I don't want to say particle. So the plum pudding model has the positive sphere and the nuclear model has the positive nucleus. What else do they have in common? Well, they both have no charge overall, because the negative electrons are cancelled out by the positive sphere in the plum pudding model, and the negative electrons are cancelled out by the positive nucleus. So no overall charge. So now let's look at the plum pudding model. What does the plum pudding model have that is different to the nuclear model? Well, let's look at the electrons. They are randomly scattered, whereas in the nuclear model they are orbiting the nucleus. So electrons are randomly scattered, whereas in the nuclear model electrons orbit the nucleus. What else do we have? So we can say that the nuclear model is mainly empty space. We can say that the nuclear model has a positive nucleus. Whereas the plum pudding model has a positive sphere. We can also say that neither of them have any neutrons. So they both have negative electrons, they both have something that's positively charged, they both have no charge overall, because if they've got something negative, something positive, that cancels them out. They both contain no neutrons. The nuclear model has electrons that orbit the nucleus. It's mainly empty space and it has a positive nucleus, whereas the plum pudding model has no nucleus. I'm just going to add that actually, no nucleus. Instead, it has a positive sphere of charge with electrons that are randomly scattered within it. Now, if you are asked to compare the two models, then a double bubble map is an excellent way to sort of construct your answer. And you could very quickly say the plum pudding model and the nuclear model both contain negative electrons. They both contain something that is positively charged. Overall, they have no charge, and neither of them contain any neutrons. The Plum pudding model has randomly scattered electrons, whereas the nuclear model, the electrons orbit in around the nucleus. The Plum pudding model has no nucleus, but does have a positive sphere of energy, whereas the nuclear model has a positively charged nucleus, and the nuclear model is mainly empty space. So a double bubble map is a really excellent way of sort of putting together that comparison between the two different atomic models that you need to know.